Hi, welcome back to this video on Applied AI. The topic today is what is a vector database and why would I use one? The objectives, I hope to let you come away in a very short period of time with a conceptual understanding of what a vector database is, why you would connect an LLM and a vector database, what you gain by doing that. And I'll try to provide some memorable analogies along the way to help with the understanding. So a little bit about me. My name is Dave Sisk. Have a bachelor's in engineering from a couple of decades ago. Done a couple of decades of work with data and databases. Fairly recent master's in data science and a pivot toward artificial intelligence, machine learning, data science, and other topics that would fall under Applied AI. So let's jump right in. So first, what is a vector embedding? What exactly are we talking about? Let's even take a step back from that. And what is a vector? It's just an array of numbers. Essentially, in a nutshell, that's it. It serves some purpose. A vector embedding, in the scope of what we're talking about today, is an array of numbers that describes arbitrary characteristics about a passage of text. That's what we're focused on today. So a very good analogy here is to think of your location as a two-dimensional vector embedding. You've got longitude and latitude, so that's two dimensions. You can think of it as a vector embedding that describes something about you. Keep that thought in your mind. Now, where location really only has two dimensions, most of the large language models, the LLMs that we're talking about, have hundreds of dimensions. GPT-3, 1536, two of the free open source, large language models from GPT for all and, Hugging Face. We're talking hundreds of dimensions instead of just two, right? So distinction to make. But we'll use location as a way to do examples. So let's continue with that. So what do we mean by a vector search? What we're focused on with a vector search is determining the distance between vectors. In a nutshell, that's exactly what it boils down to. So, for instance, you could say if you have a location vector that has latitude and longitude, you could say, how far is Savannah, Georgia from Raleigh, North Carolina, for instance? And you could do Euclidean distance where you subtract one latitude from the other and you square it, and you subtract longitude and you square it, and you add those two and you take square root. That gives you a number, 4.43 roughly, and that translates to about 300 miles, which is pretty much, that's correct in a straight line. So that's an example. It's just an equation to find Euclidean distance. And the same is true for the other distance measurements, which are cosine and dot product distance. Those are also just a mathematical calculation to determine the distance between two vectors. When we talk about a special case of vector search called vector similarity search, what we usually mean there is a k-nearest neighbors query. An example of that is show me the three international airports closest to Savannah sorted by least distance. That is the essence of a KNN query. When you generalize that, you're still looking for smallest distance. It just may be the distance calculated from 1,024 dimensions instead of only two dimensions. That's really the only difference. It's the same math, there's just more of it. At a low level, we want these KNN queries to be satisfied by an approximation method. And that approximation method is generally, the most popular one is a hierarchical navigable small world, or HNSW search. And it's kind of it's a flavor of multi-level gradient descent for KNN approximation. Let's continue. So, okay, now we know what a vector is. We know what a vector embedding is. We know what a vector search and a vector similarity search is. Where does a vector database come into this? Well, it's a data store that can obviously store vector data, but that's not really the main point. You can store vector data in a text file, and that doesn't really buy you much. The important part here is that a vector store knows how to do a KNN search, hopefully using an HNSW algorithm so that it can handle very large data sets and still return answers to that KNN search in a very short period of time, or at least a reasonable period of time. So examples of vector databases, one commonly used in this area of work is ChromaDB, which is a local, it's a simple free local storage engine. Postgres has a vector extension called pgvector that's been around for about 4 years. There's Pinecone, which is a purpose-built SaaS offering. There's actually quite a few others. We won't go into too much detail on this because I want to keep the presentation short. So, vector DBs and LLMs, why would you connect them? The answer here is that LLMs output vector embeddings, and vector DBs store, and most importantly, are able to query efficiently vector embeddings for distance. That is the point of connecting the two. When you connect them, you provide a means for the LLM to not only have long-term memory, but it's also a means for dynamic customizations by making data, your actual your transactional data, visible to the LLM to use in decisions. That's the main point. This is actually a very important topic, especially right now. It's called RAG, Retrieval Augmented Generation. That is the concept of connecting an LLM and a vector data store to gain some capabilities in both, make both of them useful. So nothing's better than an example. So let's walk through a very quick example here of a KNN example where you would pair an LLM and a vector data store, matching resumes with jobs. So the first step, you would run the text of the job descriptions through an LLM to calculate vector embeddings for the full job description text. Then you store those vector embeddings plus the full text in a vector data store. That is essentially the long-term memory for that LLM. Then, let's say a new resume comes in. Okay, you want to see which jobs is this a good match? Which jobs are the best match for this? So you could hand the text from that resume to the same LLM, get the calculated vector embeddings, and then go to the data store and query it with that vector from the resume to say, show me the job description vector embeddings that are the closest distance or the nearest distance to this resume vector embedding. There it is in a nutshell. That is a KNN search, and if we do that with a very efficient approximation algorithm, underneath the covers like HNSW, you should get a very quick response. You want this to happen ideally you want this to happen in sub-seconds rather than minutes or hours or days or something like that, right? So why do we need a vector data store? It gives the LLM long-term memory, and it provides the capability to do the KNN search, and that's a very important capability. So the important take-homes. What's vector embedding? It's a compressed representation of a text passage. The analogy, the thing I would like you to think of when you hear this is, your location expressed as the vector embedding of latitude and longitude, a two-dimensional vector embedding. KNN search, think of the analogy of what are the top 3 international airports closest to my city. That's a very good example of a KNN search. A vector data store, what you should get here is that it stores vectors. That provides the long-term memory, and it's able to do the KNN distance calculations very efficiently. That's the main thing you should remember. Linking LLMs and vector data stores, you can do that manually. You can do it with frameworks like LangChain. But the point of doing that is that you give the LLM long-term memory and you give it access to the data to actually make decisions from. So, thank you for watching. I hope this was informative. Leave a comment, just to let me know if you think I achieved the stated objective. Thank you for watching, and have a wonderful day.